So now, so a vector is a directed line segment. And a vector has an initial point and a terminal point. And the way that we denote a vector is with a letter. And we write the, sometimes we write the initial point and then the terminal point with a line over it. Magnitude is the length of the vector. And we denote the magnitude with bars around the actual vector. So this doesn't mean absolute value, it means the magnitude. And the direction of a vector is the slope or the angle of the vector. No, you don't. Okay. So you can have two equal vectors that are not like right on top of each other. So as long as your vectors have the same exact direction and length, they're both equal to each other. So you can move vectors all around the place. As long as they're shooting off in the same direction and have the same exact length, they're equal to each other. So we have here vectors that have the same length but different directions. Over there we got vectors same length, opposite directions, and then the last one there we got same direction but different lengths. Okay, so we're going to see all different types of vectors, but the whole point of this slide is so that you know that you can have vectors in different places, but they can actually be equal to each other as long as they have the same length and the same direction. So let's talk about example number 1. Okay, and I know I have all my work here, but it's actually a pretty easy example. We want to show that these two vectors here are equal to each other, vector u and vector v here. And in order to show that the two vectors are equal to each other, you have to prove that they have the same length and they have the same direction. So the first thing that I did is I found the length of the vector by using the Pythagorean theorem, essentially. So what I did is I made right triangles, and I found the legs of the two triangles, and I used the Pythagorean theorem to find the actual length of the vector. So if you make these right triangles, you can see here that the vector represents the hypotenuse of the right triangle, and so if you solve for your c value, a squared plus b squared equals c squared, then you'll end up finding the length of the vector. And then from there, I went and found the slope of vector u and v by using the rise over the run. Both vectors have a slope of 2, so they both have the same magnitude, they both have the same direction, they're both equal to each other. So here we have the component form of a vector where the initial point is at 0, 0. So as if vector v is, if v is a vector in the plane equal to the vector with initial point 0, 0 and terminal point v1, v2, then the component form of v is shown here. The way that you show the component form of a vector is with these, I want to say like these half inequality signs, with the horizontal component and the vertical component. So let me give you a quick example here. Say we have the initial point at 0, 0 and the terminal point at 3, 4. Then we would have the terminal point out here at 3, 4. And we would go from the initial to the terminal like so. And the vector in component form would be represented as 3, 4. Okay? So this is known as the component form of a vector. And so in our next example, we're going to look at different types of component form. Different vectors with we're gonna get into some different, what am I trying to say here? Goodness gracious. Here we have these different vectors with different component forms, and I actually have all the vectors drawn for us already. Due to time, I'm just going to explain them once again. So here we have 3, 4. The 3 corresponds to the horizontal component, the 4 corresponds to the vertical component. So your initial point is at 0, 0, and you go out horizontally 3, you go up vertically 2, 4. Vector u, I put that one in red. I should probably talk over my computer so everyone can hear. Vector u here in red, we start off at the initial at 0, 0. We go out a distance of -2. We go up 3. C, component form is -3, -4. And we start at 0, 0 for initial point. We go out -3. We go down -4. Last one here, 2, -5. Start at 0, 0, go out to 2, go down to 5. Now, one thing that you should pay attention to here is that if your horizontal component is positive, your vector is going to shoot off in the positive x direction. If your vertical component is positive, it's going to shoot off into the positive y direction. If you look here at C, we have a negative horizontal and vertical component, and so the vector shoots off into the negative x and negative y direction. Okay? Are we good on that? Next one. Okay. So we can have a vector that doesn't have its initial point at 0, 0. So if your vector is not at 0, 0, the way that you would find the component form of the vector is by subtracting the 2 x values from each other and subtracting the 2 y values from each other. You want to think terminal minus the initial, okay? So your terminal point being here at Q, your initial being here at P, you would subtract the terminal point x value from terminal minus the initial x value point, okay? And you do that with y as well, the terminal y minus the initial y, okay? All right, so we want to find the component form of vector PQ, where P is -3, +4, and Q is -5, +2. So let's go ahead and plot those points and draw our vector. We have -3 and +4, this point here, and that represents our initial point, because here we start off with P. And then Q is -5, +2. So we go out -5, and then +2 is this point here. So this is the Q value here. So vector PQ goes in this direction, like so. So one thing I know about this vector is that it's shooting off into the negative x and negative y direction. So that tells me that the component form, I know that I'm going to end up with a negative horizontal and vertical component, okay? But to find the actual component form, we subtract the, we take the terminal point, terminal x value, and subtract the initial x value. And we take the terminal y value and subtract the initial y value. So we have a -5 plus 3, which gives us a -2, and then we have a 2 minus 4, which gives us a -2. So the component form of this vector is -2, -2. Now, I told you guys that you can move a vector all around and it will still be equal to the same thing, right? So I could take this vector and put this vector right over here with the initial point at 0, 0, and we see that we do shoot out to that point -2, -2, right? So we can move that vector all around and it still is the same vector. Okay? Good? All right. So this next piece here is all about finding the actual magnitude or the length of a vector that doesn't have the initial point at 0, 0. And all it is really is the distance formula, which is just the Pythagorean theorem. So don't let this formula scare you. Our next question involves finding the magnitude of that vector that we just found for example 2a. So 2b is just finding the magnitude of that vector from example 2a. So what I want to do is I just want to jump back to 2a and look at finding the actual magnitude of this vector. Now you guys, it's pretty easy if you just think about this in terms of a right triangle here. If you look at this as a right triangle here and try and find the legs of that triangle, well, how would you find the horizontal component? You would take the difference in the x values. We've already done that here, right? That actual length is a 2. How would you find the difference in the the vertical components? You would take a difference in the y values. We've already done that. That distance is a 2, right? But we see that in the component form here. So we would end up taking the square root of, using the formula, you take your components, your horizontal and vertical component, square them, you add them up, and take the square root of that. And literally all I'm doing here is using the Pythagorean theorem, right? So this is equal to the square root of 8, which is approximately equal to like 2.8 around there, right? You know, the square root of 9 is 3, so this is about, I'm going to guess, 2.8. All right? Okay. So this next one here is about vector addition. You can add two vectors up by adding the horizontal component to the horizontal component and the vertical component to the vertical component. So this slide here is all about just viewing the addition of two vectors. This is like the geometric representation of the addition of two vectors. So say we're adding two vectors together, and you want to look at how what that looks like visually. You would position vector u and v so that the terminal point of u coincides with the initial point of v. And remember that you can move the vectors around. So even if they aren't touching right off the bat, you could make them touch, right? You could move the vectors around so the initial touches the terminal. The resulting vector will be u plus v, and it extends from the initial point of u to the terminal point of v. So it's just a geometric representation. So in this example, 3a, we're going to find the component form of the addition of these two vectors, and I'm going to show you what they look like geometrically. So let's go ahead and add them up. We have u, which is a minus 1, 3, plus we have v, which is 4, 7. If we add them up, we add the horizontal component to the horizontal component and the vertical component to the vertical component. So we have 3, 10. That was easy. Let's go ahead and understand the geometric meaning behind all of this. Okay, so we have minus 1, 3. And so that is this vector right here. I'm going to go minus 1, 3. Okay, and then we have the other vector is 4, 7. So that is this vector in blue. I'm just going to pull that over here. we have a 4, 7, so 1, 2, 3, and 4, and then we have 3, 4, 5, 6, 7. And if we take the terminal side of vector u and connect it to the initial side of v, then the resulting vector u plus v will go from the initial of u to the terminal of v. So this next section is about scalar multiplication, and a scalar will stretch a vector or shrink a vector or change the direction of the vector. And a scalar is a numeric value that is multiplied on the vector, and we will distribute that scalar into the horizontal and the vertical component of the vector. So, here the example is done. We have vector u and vector v once again. We want to find the component form of the vectors when we have a 2u plus minus 1v. So here we have 2 times the component form of u plus minus 1 times the component form of v. So we distribute in the 2, we distribute in the minus 1, and then we add the horizontal component to the horizontal component and the vertical component to the vertical component, and our resulting vector is shown here. So one thing that I notice is that when we added u and v before, we ended up with a vector that was 310, and 310 shoots off in the positive x, positive y direction, right? And now we have this vector that shoots off in the negative x, negative y direction. This is making lots of sense to me because one of our vectors, we've multiplied it by a negative, and it changed the direction of that vector. So that was just a side note, me thinking out loud. Let's move on to the unit vector. Okay, a unit vector is a vector that has a magnitude that is equal to a 1. And the way that we find a unit vector is by taking the component form of the vector and multiplying it times 1 over the magnitude of the vector. So I'll show you the next example here, example 4. I've actually already done it, and so I'll just explain it. We want to find a unit vector in the direction of vector v and verify that it has a length of 1. So the first thing that I've done here is I've found the magnitude of vector v, which is the square root of 13. And then what I've done is I've taken the component form and I divided by the magnitude, which is the same thing as saying 1 over the magnitude times the component form of the vector. So from here, I've distributed in 1 over the magnitude, and I end up with the component form as minus 3 over root 13 and 2 over root 13. And to verify that it has a length of 1, what I've done is I've taken the component form and squared the horizontal and vertical component, added them up, and then took the square root of them. So minus 3 over root 13 turns into 9 over 13, plus we have 2 over root 13 squared, that turns into 4 over 13. We add up the numerators, we get 13 over 13 is 1, and then the square root of 1 is equal to a 1.